Hi everyone, my name is Luís Pereira. I am a graduate student at the Soil Science and Plant Nutrition graduate program in the Federal University of SOUZA, and today I'm going to present to you the work entitled Modeling and Mapping Superficial Soil Texture Through Machine Learned and Limited Legacy Data. Soil is the integrating sphere of the Earth's critical zone, and soil texture regulates main biological, physical, and chemical processes in the soils. In this sense, environmental models, land policies, and land management should consider soil texture, but spatial information with good regional and local consistency is still lacking for this kind of soil properties. So it is from some struggles we are facing in digital soil mapping. For example, no standard data sets, unavailable locations, of the locations of the samples in these data sets, low sample density of the data sets, and temporal variability inside the data sets. So how can we map using this kind of data set, limited data set? Well, in the last years, a lot of new approaches and technologies was developed to try to do this. And the most effectively ones are related to artificial intelligence, machine learning, and deep learning. In this study, we will use machine learning to try to solve the problem related to low sample density in our data set. So our aims are assess machine learning techniques in mapping surface soil texture using limited legacy data, and map the surface soil texture in Minas Gerais state, providing spatial information with good consistency and no uncertainties. The region that we have studied was the Minas Gerais state. We got a data set with 668 samples that contains coarse sand, fine sand, silt, and clay contents at the topsoil. It was got from SOUZA et al. 2015. They used standard methods for sampling and soil analysis. So the unique problem in our data set is the low sample density problem. The data set has a sample density of approximately 0.001 sample per square kilometer. But on the other hand, we have a good spatial distribution of the samples. We split this data set into training and test data sets. Training, we used 75%, and for test, 25% of the samples. Our covariates were based in the SCORPAN model, and we got climate information from WorldClim, parent material from the Geological Survey Institution of Brazil, soil classes from Federal University of SOUZA, soil measure from Era 5 land, and relief from NASA DEM, the digital elevation model, and morphometrical covariates that were got from the processing of this digital elevation model. All the covariates were harmonized to 500 meters of resolution. That was also the final resolution of our maps. After that, we applied sequential predictor selection. It was made to avoid unnecessary complexity of the models, and it was made in 2 steps. Spearman's correlation from a pair of covariates with more than 0.595 of correlation. We removed the covariate that have the biggest correlation with the global data set. And the second step was recursive feature elimination. That is an algorithm to perform a selection of the covariate set which produce the lowest mean absolute error regarding a cross-validation in 10 folds in our study. We used 5 algorithms. They were random forest, cubist, multivariate adaptive regression splines, support vector machine using radial kernel, and stochastic gradient boosting machine. And we performed 100 runs per algorithm, changing always the split of the data set. It was made to access the variability and selecting and to select the best model to predict the maps. Our modelings here were performed in the CARE package in the R environment. Our analysis of consistency and uncertainties was based for the outputs, and we used average maps, the coefficient of variation of the contents, and the sum of the modeled contents, and the silt by difference calculation that is calculated taking 100% and taking out the sum of the clay, fine sand, coarse sand modeling contents. Here we have the first result. We got that random forest present the smallest errors and the biggest coefficient of determination. Let me turn on my pointer. We can see these in these head circles that are marking the random forest. Our models show a no overfitting. It's good. You can see it comparing the values of the training with the values of the external test. And the sand fractions presented the worst performance in terms of the coefficient of determination. It indicates that merging these two classes, coarse sand and fine sand, could be great to improve the mapping. The mapping of a single class that could be called sand, for example, only sand. Clay presented biggest errors, but it's normal because clay also presented the biggest content, so it's okay. And in general, the models presented low errors. For the random forest here, you can see that the values ranged from 5 to 16%. That's a good value of error regarding the literature. Here we have our second result. Our maps present low coefficient of variation values and good consistency for the random forest models. You can see it here. Our coefficient of variation are mainly under 15%, and in terms of consistency was good too. You can see here that the values of sum of modeled contents are around 100%, which was great, and there are very low values of very low occurrence, of unrealistic values for silt. You can see here that negative values occur only here in this small point. Also, we have an interesting result that the map of calculated silt is pretty similar to the modeled map for silt, so shows also good consistency, and areas with high content of clay are corresponding to areas with low content of fine sand and another fractions at all. Only 10 to 15 predictors were needed to stabilize the performance of the models. The most important predictors vary among particle size involving all SCORPAN factors. It indicates that our model is considering the interaction between the soil formation factors to predict what's another good indicator of consistency of the models. So our conclusions are that machine learning techniques can produce fair, consistent maps for superficial texture and the associated models uncertainties, even using limited legacy data. And random forest was the best model to map all particle size. The most important predictions were distributed across all SCORPAN factors. And I would like to acknowledge CAPS and NPK for supporting this research. My contact is below in the screen. And thank you so much for being here. I am available in the chat for answering questions.